So today we're going to be talking about the logic of quantified statements. All right. Predicates and quantified statements, part 1. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. The domain of a predicate is the set of all values that may be substituted in place of the variable. Sorry. And so let P of x be the predicate. X squared is greater than x with a domain, the set of R for all real numbers. Write out P of 2, P of 1/2, and P of minus 1/2 to indicate which of these statements are true and false. Of course, 1/2 squared is less than 1/2, as well as minus 1/2 is less than 1/4, so that would be true. And P of 2 squared is greater than 2, so the first and third are true. Second one is false. So if P of x is a predicate and it has x as domain, the truth set of P of x is the set of all elements of D that make P of x true when they are substituted for x. The truth set of P of x is denoted x is an element of D where P of x is true, such that P of x is true. So let Q be the predicate, n is a factor of 8. Find the truth set of Q of n. If the domain of n is positive integers, and if z is the set of all integers. The truth set of Q would be, 1, 2, 4, and 8 for positive integers, and that plus minus 1, minus 2, minus 4, and minus 8 for the set of all integers. So, yeah. It's the truth set because these are exactly the positive integers that divide 8 evenly. And this is the truth set if the domain is the set of all integers. So the universal quantifier. One sure way to change predicates into statements is to assign a specific value to their variables. For example, if x represents the number 35, the sentence x is evenly divisible by 5 is a true statement. Another way to obtain statements from predicates is to add quantifiers. Quantifiers are words that refer to quantities such as some or all and tell how many elements a given predicate is true. The symbol the upside down A is called the universal quantifier. Depending on the context, it can be read as for every or for each, for any, given any, or for all. Another way to express the sentence every human being is mortal, or all human beings are mortal, is to write The upside down A, human beings, X is mortal. It would read for every human being X is mortal. If you let H be the set of all human beings, then you can symbolize the statement more formally by writing for all X that are elements of humans, of all humans, X is mortal. Definition. Let Q of X be a predicate and D the domain of X. A universal statement is a statement of the form upside down X is element of D, comma, Q of X. It is defined to be true if and only if Q is true for each individual X in D. D cannot be an infinite set. It has to be a finite set, I believe. It is defined to be false if and only if Q is false for at least one X in D. No, D doesn't have to be a finite set. A value for X for which Q of X is false is called a counterexample to the universal statement. So let D be 1, 2, 3, 4, 5. And consider the statement for every X that's an element of D, X squared is greater than or equal to X. Consider the statement for all X who's an element of real numbers, X squared is greater than or equal to X. Find a counterexample to which for which this statement would be false. A value of X where the is a positive real number less than 1 would be a counterexample. For every X in set of D, X squared is greater than or equal to X. The inequalities shown below show that X squared is greater than or equal to X is true for each individual X in D. Therefore, that statement here is evaluated as being true. Finding a counterexample, like in the second statement, renders this statement false. So you have the universal quantifier. Now we have the existential quantifier, the upside down E. The upside down E denotes there exists and is called the existential quantifier. For example, the sentence, there is a student in Math 140, can be written as, there exists a person, P, such that P is a student in Math 140. Or more formally, upside down P is the element of P such that P is a student in Math 140, where P is the set of all people. The domain of the predicate variable is generally indicated either between the E symbol and the variable name, or immediately following the variable name and the words such that are inserted just before the predicate. So, let Q of X be a predicate and D the domain of X. An existential quantifier is a statement of the form E, there exists an X that's an element of D such that Q of X is true. It is defined to be true if and only if Q of X is true for at least one element in D. It is false if and only if Q of X is false for all X in D. So, consider the statement. There exists M that's an element of positive integers such that M squared equals M. Is that true? Is that true? There exists a number M in the element of that's an element of positive integers such that M squared equals M. Yeah, 1. Yeah. That's all you need to show is one example of it being true, and then therefore the whole statement is true. Now, the second example is for the numbers 5, 6, 7, and 8. You have to show by exhaustion that for all these elements, M squared does not equal M. So you go through each element of the set, and you can show that the overall statement is false. Now, we've been going back and forth between formal and informal language a bit for so far this semester. It is important to be able to translate between formal and informal language, especially when trying to make sense of mathematical concepts that are new to you. It is equally important to be able to translate from informal to formal language when you're when thinking out a complicated problem. So this is a skill that you need to develop. Rewrite the following formal statements in a variety of equivalent but more informal ways. Do not use the inverted A or inverted E symbol for that. For every real number x, x squared is greater than or equal to 0. It's less formal. Still using the variable x, but for every real number x, x squared does not equal minus 1. And finally, there exists a number m, a positive integer m, such that m squared equals m. Now, all of these statements are true, but the idea is to think about them in formal and informal terms. So, I went through these. Any real number has a non-negative square. Square of each real number is non-negative. All real numbers have squares that do not equal minus 1. There's positive integers whose square is equal to itself. Some positive integer equals its own square. Some positive integers equal their own squares. Different ways of doing it informally. Now, trailing quantifiers. You don't have to put the quantifier first. For example, for any integer n, 2n is even. You just flip the phrases, the clauses around and say 2n is even for any integer n. The quantifier follows the predicate. There exists at least one real number x such that x squared is greater than or less than or equal to 0. How would you put that in with a trailing quantifier? X squared is less than or equal to 0 for at least one real number x. Okay? And these rewrite these statements formally using quantifiers and variables. All triangles have three sides. Inverted A, small t is an element of t, such that t has three sides, and big T is the set of all triangles. And similar for no dogs have wings. Some programs are structured. There exists a P whose element, a program whose element of all programs, such that P is that program is structured. Yeah. But yeah, go back and forth between formal and informal language. When speaking to someone, you could use the informal, and when writing, use the formal. Universal conditional statements. So, a reasonable argument can be made that the most important form of statement in mathematics is the universal conditional statement. For all x, if p of x, then q of x. So, write the following statement informally without quantifiers or variables. For all x that are elements, for all real numbers x, if the number is greater than 2, then the square of the number is greater than 4. You have two clauses there. The x is greater than 2 and the x squared is greater than 4. So if a real number is greater than 2, then its square is greater than 4. Whenever a real number is greater than 2, its square is greater than 4, and so on and so forth. So it's another form of the if-then statement that we learned last chapter. Let's see here. Write each of the following statements in the form upside down blank, if blank, then blank. For all integers, for all real numbers that are integers, for all real numbers, if the number is an integer, then it is a rational number. So for all x is element of R, if x is element of z, then x is an element of Q. Remember Q, the set of rational numbers? All bytes have 8 bits. No fire trucks are green. So similar type of situation for each, for all elements in the domain. If the first phrase is true, then the second phrase is true. And these are the solutions for that. For all real number x, if x is an integer, then x is a rational number, or that statement, symbolic statement there. If x is a byte, then x has 8 bits. For all x, if x is a fire truck, then x is not green. It is common to omit the explicit identification of the domain of predicate variables in universal conditional statements if it is obvious. And it is not always obvious. So in the first one, you state the domain of x, and in B and C, you don't have to do it. You don't have to do it strictly. Equivalent forms of universal and existential statements. Two statements. Real number x, if x is an integer, then x is rational, and x is an integer, x is rational, mean the same thing because the set of integers is a subset of real numbers. So you can have both have the same formal translation, but it can always be written in the form of this, where D is a subset of U for all values of the variable x that make P of x true. Conversely, the statement of the form for all x is an element of D, then Q of x can be written for all x. If x is in D, then Q of x is true. Rewrite the following statement in the two forms. All squares are rectangles. For all x, if x is a square, then x is a rectangle. For all squares, x is a rectangle, right? Is that what they're looking for? Yeah. For all squares x is a rectangle. If x is a square, then x is a rectangle. So let's see here. We know what a prime number is. Consider the statement: there's an integer that is both prime and even. Let prime n be n is prime, and even n be n is even. Use the notation prime n and even n to rewrite the statement in the following terms. There exists an n such that prime n and even n. And there exists an even n, or a prime n, such that even n. Sound good? Or they flipped it around. I flipped it around, but there exists n such that prime n and even n. And you could do that because the conditional that we learned in the previous chapter is prime n and is prime or one value and the next value. The bound variables and scope. So bound variables, okay, let's use an example here. Consider the following statements. For every integer x, x squared is greater than or equal to 0. And 2, there exists a real number x such that x cubed is 8. Both 1 and 2 call the variable x, but the x in statement 1 serves as a difference function from the x in statement 2. So we say that the variable x is bound by the quantifier that controls it, and its scope begins when the quantifier introduces it and ends at the end of the quantified statement. So you can confuse people by using x in multiple places in a complex structure by using it in different scopes at different places in the structure. Implicit quantification. So consider the statement, if a number is an integer, then it is a rational number. As shown earlier, the statement is equivalent to a universal statement. However, it does not contain the telltale word all, or every, or any, or each. The only clue to indicate its universal quantification comes from the presence of the indefinite article a. There is an example. This is an example of implicit universal quantification. There is a number. If a number is an integer, then it is a rational number. So existential quantification can also be implicit. For example, the statement, the number 24 can be written as the sum of two integers. The can be is the indicator of the existential quantification. So watch out for that word to mean existential quantification. So there exists an even integers m and n such that 24 equals m plus n. The notation P with the double line arrow to Q means that every element in the truth set of P of Q, or P of X, is in the truth set of Q of X, or equivalently, for all X, P of X implies Q of X. The notation with a double-ended, double-lined arrow between the P of X and Q of X means that P and Q have identical truth sets, or equivalently, for all X, P of X is biconditionally related to Q of X. So let Q of n be n is a factor of 8. R of n be n is a factor of 4. Let S of n be n is less than 5 and n is not equal to 3. So suppose the domain of n is the set of all positive integers. Use the symbols to indicate the relationships among Q of n, R of n, and S of n. Well, what was that definition again? Every element in the truth table of the first one is in the truth set of the second set. So R of n is in the set, is the subset of Q of n, so that would be the single arrow. N is a factor of 4, and n is less than 5, and n is not equal to 3. They're the same, so they can use the double arrow. So therefore the single arrow going from the 4 to the 8, and the double arrow going from the factor of 4 to this quantity, and then this can, because this is the same as this, you can substitute n is less than 5 and n is not equal to 3 is the single arrow to n is a factor of 8. Tarski's world. I'm kind of ambivalent about this being included in the slides, but Tarski's world is a computer program developed by some information scientists to teach principles of logic. It is a arrangement of objects in a two-dimensional environment, and we'll come back to this figure in just a minute. The configuration can be described using logical operators. Notation is such as triangle. It means that x is a triangle. Blue is meaning blue of y, meaning y is blue, and right of means of x and y means x is to the right of y. Individual objects can be given names such as A, B, C, or D, or whatever. Determining the truth or falsity of each of the following statements, the domain for all variables is the set of objects in the Tarski world shown in 3.1.1. Let's see here. For all t, if t is a triangle, then t is blue. If for all of x, if x is blue, then x is a triangle. You can refer back to the diagram on the previous slide before to determine which one of these are true and which are false. It's just kind of a game that you can play. I invite you to go through the slides after I post them this evening to go through all these. The statement is true because every triangle is blue. Statement is false because E is blue and it's not a triangle. Let's see here. C is true, D is false, so on and so forth. And that about wraps up this section. Take a brief break. And find the second section. All right. More of the same. Logic of quantified statements. Come on. Screen is not cooperating today. All right. Okay, predicates and quantified statements, part 2. Negations of quantified statements. A lot of the same rules apply that we applied to regular logic in the second chapter. The negation of the form for all x and d, then q of x is logically equivalent to the statement of the form there exists an x in d such that not q of x is true. Symbolically, that mishmash of stuff, the negation of a universal quantifier is an existential quantifier such that the inverse of the predicate is true. So, the negation of a universal statement is logically equivalent to an existential statement. Note that when we speak of logical equivalence for quantified statements, we mean that the statements always have the identical truth values, no matter what predicates are substituted for the predicate symbols, and no matter what sets are used for the domains of the predicate variables. Negation of an existential statement. If it's in the form, there exists an x and d such that q of x, it is logically equivalent to the statement there for all x and d, the inverse of q of x is true. So for all x in d, q of x is false. There doesn't exist an example where q of x is true, is the equivalent. The negation of an existential statement is logically equivalent to the universal statement. None are, or all are not. There doesn't exist. Formal negations for the following statements. For all primes p, p is odd. There exists a prime p such that p is not odd. There exists a triangle T such that the sum of the angles of T equals 200. For all triangles T, the sum of the angles of T are not equal to 200, or something along those lines. For all triangles T, does not equal 200. And there exists a prime P such that P is not odd. So, writing negations of statements can be tricky. Rewrite the statement formally and then take the negation and then translate it to an informal form is a better strategy. Rewrite the following statements formally, then write the formal and informal negations. No politicians are honest. I think that's called a tautology. Always true. Now, for all p, there exists a p in politicians where p is honest. It would be the negation. The number 1357 is not divisible by any integer between 1 and 37. The inverse of that would be, or the negation of that would be, let's see here. For all there exists a number between 1 and 37 such that 1357 is divisible by it. Is that right? There exists an integer n between 1 and 37 such that 1357 is divisible by n. Some politicians are honest. The statement has trailing quantifier. Formally written, it becomes that. But an informal version of the negation is this. The number 1357 is divisible by some number between 1 and 37. Negations of universal conditional statements. It basically does the same type of thing. For all, the negation of for all x, p of x implies q of x. The negation would be for there exists an x such that p of x does not imply q. But the negation of an if-then statement is logically equivalent to an and statement. So you could write it as there exists an x such that p of x and not q of x. So that's the because that's the negation of the conditional that we learned in last chapter. Let's see here. Yeah, the negation of a universal conditional statement, therefore, is that. There exists an x such that p of x and not q of x. Formal negation for the statement A and an informal negation for statement B. There exists a P such that if P is blonde, then P does not have blue eyes. Inverse of if a computer program has more than 100,000 lines, then it contains a bug. I think that's always true. Anyway, so there exists a program such that the program has more than 100,000 lines and it does not contain a bug. So you keep the first part of it and then invert the second part to negate the statement. Let's see here. There's at least one program that has more than 100,000 lines and does not contain a bug. So the relation among the universal quantifier, the existential quantifier, and an OR. All right. The negation for all statement is there exists, and the negation of a there exists statement is a for all statement. These are analogous to De Morgan's laws. In a sense, universal statements are generalizations of and statements, and existential statements are generalizations of or statements. And that could be seen in this example. For all x, an element of D, Q of x is the equivalent to Q of x1 and Q of x2 and Q of x yada 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 to Q of xn across the domain D. And it gives an example with binary digits. For all binary digits, x times x equals x. 0 times 0, and you can see that that's true because 0 times 0 is 0 and 1 times 1 is 1. So it can be written as Q of 0 and Q of 1. The existential statement is the equivalent of there exists a Q of x1 or Q of x2 or Q of yada 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 to Q of xn. Just have to show that one of the, for this to be true, you just have to show that one element of the sequence of ors is true. So for binary digits, let Q of x be x plus x equals x. It is true because 0 plus 0 equals 0, or 1 plus 1 equals 1. This is false, but this is true, making the whole statement true. And it can be written as Q of 0 or Q of 1. Vacuous truth of universal statements. This is best shown with an example. Suppose the bowl sits on a table and next to the bowl is a pile of 5 blue and 5 gray balls, any of which may be placed in the bowl. If 3 blue balls and 1 gray ball are placed in the bowl as shown, then the statement all balls in the bowl are blue would be false, since 1 is gray. Kind of a gimme. Okay, now suppose that there's no balls placed in the bowl. All right. All the balls in the bowl are blue. True or false? Well, if the statement is if the statement is going to be false, its negation is true, and its negation is there exists a ball in the bowl that is not blue. But the only way this negation can be true is for there to actually be a non-blue ball in the bowl, and there is not. So the negation is false. So the statement is true by default, or vacuously true. In general, a statement of the form for all x in D, if P of x then Q of x, is called vacuously true or true by default if and only if P of x is false for every x in D. So, harkens back to the conditional, the vacuously true conditional statement from chapter 2. Variants of the universal conditional statements. The contrapositive is like the contrapositive of the conditionals from chapter 2. You invert and flip the predicates. So if P of X, then Q of X. The contrapositive is if not Q, then not P. The converse is the statement where you just flip the predicates. If Q, then P. And the inverse is if not P, then not Q. Much like the same forms in the conditional we saw in chapter 2. The only difference is you're adding the universal quantifier out front. Contrapositive, converse, and inverse of the following statement. If a real number is greater than 2, then its square is greater than 4. Contrapositive is if a number's square is not greater than 4, then the real number is not greater than 2. Converse would be if the square of a number is greater than 4, then the number is greater than 2. And the inverse would be if a number is less than 2, less than or equal to 2, then the square is less than or equal to 4. I think I got those right. Yeah. If the square of a real number is less than or equal to 4, then the number is less than or equal to 2. Yeah. Inverse. If x is less than 2, then less than or equal to 2, then x squared is less than or equal to 4. Note that solving this example, we have used the equivalence of x is not equal to a and x is less than or equal to a for all real numbers x and a. Necessary and sufficient conditions, only if. Remember these from chapter 2? R is a sufficient condition for S of x means that if R of x, then S of x. If R of x is a necessary condition for S of x, means that if not R, then not S. Or, equivalently, if S, then R, because of the contrapositive. R of x only if S of x means that if not x, then not R. Again, because of the contrapositive, you could also write that as if R of x, then S of x. So, good rules to follow for writing things less formally. Rewrite each of the following universal conditional statement quantified either implicitly or explicitly. Do not use the word necessary or sufficient. Squareness is a sufficient condition for rectangularity. If S is a square, then S is a rectangle. If R, then S. Being at least 35 years old is a necessary condition for being the President of the United States. If a person is the President of the United States, then they are at least 35 years old. Using formal language, formal version If S is a square, if X is younger than 35, X cannot be the President of the United States. Or by the equivalent, because of contrapositive, if X is the President of the United States, then X is at least 35 years old. Universal conditional statement. A product of two numbers is 0 only if one of the numbers is 0. If one of the numbers is not 0, then the product of those two numbers is not 0. Kind of a contrapositive kind of a thing going on there. Yeah, if neither one of the numbers is 0, then the product of the numbers is not 0. Let's see. Yeah, if the product of the numbers of two numbers is 0, then one of the numbers is 0. At least one of the numbers. And that'll about wrap it up for these two sections. Any questions? How are we doing on time? Oh, 2:31. Oh. Plenty of time for questions. Got, what, 20 minutes? All right, well, yeah.
For the test, what points specifically? I know you said it's going to be based on chapters 1, 3.
No, 1 and 2.
Oh, just 1 and 2?
Just 1 and 2. The test is for chapters 1 and 2 on Thursday. So bring your notes. Notes are perfectly fine for your for reference for the test. So be on time. It's 15 questions, I believe. 7 points apiece, again worth a possible 105 out of 100. So study up, print out your notes, and try to be on time. Have a nice day. See you on Thursday.